Hello, this is a summary of Lecture 8 from today. We covered the Neyman-Pearson paradigm last time. In particular, we discussed type 1 and type 2 errors and also defined power. I just want to make a note that a simple hypothesis is when your null and alternative hypothesis are for particular specific values of theta. So for example, if you flip a coin with probability p heads 3 times, by saying that for the null hypothesis p is 0.5 and for the alternative p is 0.7, that's an example of a simple hypothesis. So what's more common is having an alternative which is composite, which means that there are many theta values. So the most popular example is you could have a null that's p is 0.5 and an alternative that's p is not equal to 0.5 or p is greater than 0.5. Then last time we also introduced the likelihood ratio test, which always has the form that you reject the null if the ratio of the null distribution to the alternative distribution is less than some constant c, and this constant c is determined by alpha, your type 1 error. So today we're going to give some more examples of how to find your rejection region and power. Then I'm going to introduce p-value and universally most powerful test, and then we'll talk about the duality of confidence intervals and hypothesis tests. So starting off with a good example here, it's really important to make a picture, if you can, of the null and alternative distribution. So in this example, the null distribution is just just 1 between 0 and 1, and the alternative is 2x between 0 and 1. So we can graph these here, and we're told that alpha is 0.1. So I can draw in my picture here what alpha is in purple. Alpha is going to, so I know that I can, first of all, I can see that I'm going to be rejecting to the right. My rejection region is to the right because to the right it's more likely that I have the alternative. And you can figure out exactly what the cutoff for your rejection region is because alpha is 0.1. So the area in purple has to be 0.1, and hence the cutoff has to be x is 0.9. But anyway, we can see this mathematically, and that's what we do here. So you can define your cutoff in terms of lambda, and your cutoff is 1 over 1.8, or in terms of x, in which case your cutoff is 0.9. Notice that the direction of the cutoff changes depending on what your test statistic is. The power is always given by the picture drawn here, so whatever your cutoff is, so 0.9, it's the area to the right of 0.9 under the alternative distribution. So that's shown here in green. Or you can just find it mathematically as I did here. The Neyman-Pearson lemma basically says that as far as simple hypotheses go, you can't do any better than a likelihood ratio test. So the unfortunate thing is most hypotheses aren't simple, so we don't actually use it that much, but it's important to understand as a sort of stepping stone to more complicated cases. P-value is ubiquitous in statistics. It's the probability that you get a test statistic as or more extreme than the one you observed. So just in a picture, if you have some distribution here, right, and we're rejecting to the left or to the right, let's say, then let's say that you get a TS here, then this would be your p-value. So it's the chance of getting a value as or more extreme. If you're rejecting on both sides, then like if it was a symmetric situation, then your p-value would be an area on two sides, but we'll see an example of that later. So right, so here's an example. X is normal with unknown mu, and we want to figure out two possible mu's. We observe 120. So here's a picture of all the players, right? We have alpha, power, p-value, all in this picture here. Make sure you understand. So now if you're told that you're going to reject for large values of the absolute value of t, then that would indicate that you have a two-sided test, in which case we would be rejecting to the left and right. So this is a case where p-value